Hi, good morning. Today we are going to discuss performance of transmission line in transmission and distribution. So, as of performance is considered, so the main thing that we are to focus is about the voltage regulation, efficiency, and losses. So here the transmission lines are classified into three types. One is called as a short transmission line, medium transmission line, and long transmission line. So based upon the length of the line and based upon the voltage levels, so it has been classified into short, medium, and long transmission line. So as of medium transmission line, so it has been further classified into nominal T method, nominal phi method, and N condenser method. Here, to determine the performance of a transmission line, the three parameters or the three constants plays a major role. So the constants are R, L, and C. So directly we'll go to the short transmission line. So when the length is about 50 km, up to 50 km, and the voltage level is up to 20 kV, so it has been considered as a short transmission line. In case of a medium transmission line, so kilometers of length 50 to 150 kilometers, and the voltage greater than 20 and less than 100 kV, it has been considered as a medium transmission line. Well, in case of a long transmission line that is greater than 150 kilometers length of line and greater than 100 kV, it is considered as a long transmission line. So as we have discussed, three parameters or three constants R, L, and C. So whatever will be the transmission lines is considered. So all R, L, and C will have an impact on transmission line, while we are not considering the capacitance effect in short transmission line because the length of the line is very minimum and the impact of the capacitance in a transmission line is also very minimum. Hence we are neglecting that component, while in terms of an medium and long transmission line, so we will consider all the three components and will have a derivation. So this is an important terminology, voltage regulation. So sending in voltage minus receiving in voltage divided by receiving in voltage into 100, and similarly the efficiency, so receiving in power divided by sending in power into 100, which gives an efficiency of a transmission line. So if the efficiency is nearer to 100, so the line is good, and similarly if the voltage regulation is nearer to 0%, so the voltage is also good. So this determines the performance of a transmission line. So we will have a short discussion about how the short transmission lines are considered and the equations are wrote. So consider a short transmission line that has a resistance and reactance along with a load. So this is called as an sending end area and this is called as a receiving end area. And the current I flows in the network, and correspondingly the phasor diagram has been discussed here. So always we have to consider the voltage as a reference, that is receiving inside. So as of this is considered, so receiving and data would be will have that is a load side will data will have. So with the load side data, so we can able to find so what is an voltage and the current that is received from the sending end area. So this is an phasor diagram. So voltage is a reference and this is in current, receiving in current. While in case of a short transmission line, the receiving as well as the sending end current are same. And this is called as a loss and due to resistance, and this is a loss due to an reactance, and put together this is a loss due to an impedance, and put together is called as a sending end voltage. With the help of the phasor diagram, so we will write the equations. So OC square is equal to OD square plus DC square. So with this we can formulate the mathematical formulation. With the help of this, so we will get the voltage equation as Vs is equal to square root of Vr cos phi r plus Ir square plus Vr sin phi r plus Ixl the whole square. With this we can able to find the Vs, that is in sending end voltage. So the receiving end voltage will be given. So the regulation, percentage regulation is equal to Vs minus Vr divided by Vr into 100. And similarly, the efficiency is about power delivered by power sent out. If we calculate all those things, we can get an results. So that is often short transmission line is considered. And similarly, for a medium transmission line, so there are three methods: end condenser method, nominal T and nominal phi. So in an end condenser method, the capacitance is considered at the end of the transmission line. And the resistance and inductive reactance are in the lines. In this phasor diagram is similar to the short transmission line. So reference voltage has been taken as receiving end voltage. So from that, so the receiving current has been drawn. Receiving end current. So the sending end resistance, that is sending end current along with the drop, has been drawn here, and this is an sending end current with respect to an XL reactance, and this is an total impedance losses in the transmission line, that is due to resistance and reactance. So put together is called as an sending end voltage. So we know the formula. So the capacitive current IC is equal to 2 pi FCV into R. The load current IR is equal to, so always we will consider the load current with respect to an angle, and the voltage has been referenced. So VR is equal to VR at an angle of 0 degree. Well, in case of an IR is equal to IR into cos phi R minus J sin phi R. We know that the sending end current is equal to, the current is dividing into 2 here, IC plus IR. So IR is equal to the receiving end current IR into cos phi R minus J sin phi R plus the capacitive current J 2 pi FC V suffix R. So if we manipulate all those things, so we can get an sending end current. Similarly, so the sending end voltage we know, so Vs is equal to VR plus drop across this line. So drop across this line, this is considered as an impedance plus the IS current into Ez. Okay, so if we consider all those things, so we can able to find the sending end voltage. So Vs minus VR would be VR into 100 is an voltage regulation. And this is in a diagram with respect to nominal T. So capacitance is considered the mid, and these two resistance and inductance has been divided into 2. And same calculation has been performed with respect to phasor diagram. So by next class I will draw and explain neatly with respect to the derivation. So as this is a reference video, we will take. So VR is considered as VR plus J0. So voltage is always reference, and current lags with respect to particular angle. So the formula has been given as IR is equal to IR into cos phi R minus J sin phi R. With the help of the circuit diagram, we will solve the equations. So from that we will get Vs is equal to V1 plus Is into Z by 2. The same thing, so we can able to calculate the regulations, voltage regulations and efficiency to determine the performance of a transmission line. Next, nominal phi method. So here the capacitance has been divided into 2, and the resistance and reactance are considered as in a line, but that is unclubbed, or a bulk of resistance and reactance has been considered in between the capacitance. Here also we are considering the voltage as a reference, and I lags with respect to certain angle. So and here two capacitive currents IC1 and IC2. If you solve all those things, so we can able to find the line current, sending end voltage, the capacitive current and sending end current, all those things we can able to find. So these three methods is used to calculate the performance of the lines. From this we can able to determine whether the line is under an inductive or capacitive. So based upon the angle directions, whether it is of a plus or minus. If it is of a negative, the line is considered as a lagging line, and if it is of a positive, and it is considered as a leading line. It is considered as a leading line. With this, so we can able to read the performance of transmission line. The long transmission line has been discussed in the next video, so kindly see that, so you can able to understand. We'll have a discussion, the problem discussion in the next video. Thank you for the patient listening.